You know that feeling, right? You're staring at your phone, watching the battery percentage just plummet, and you wonder, why can't this thing hold a charge like it used to? Well, that's exactly what we're digging into today. We are cracking the code on one of tech's biggest mysteries, the slow, inevitable death of the lithium-ion battery. Let's get into it.
Seriously, why is your phone's battery doomed? It's not just phones either. It's our laptops, our headphones, our cars. Every single one has this built-in expiration date. But what if there was a way to see the end coming? To predict it with, perfect accuracy?
You see, for years, trying to predict when a battery will die has been, well, kind of like throwing darts in the dark. The models that manufacturers use now are really just educated guesses. They're often super specific to just one type of battery, they take a ton of computing power, and honestly, they can be wildly inaccurate, especially when things get a little weird. And that brings us to what I'm calling the unsolved battery case. We're going to be the detectives today. The mystery's all about the complex and, let's be honest, chaotic way that batteries degrade. Why do some die so much faster than others? And why do our prediction models seem to fail us right when we need them the most?
Okay, so here's the deal with those old models. They have some major blind spots. They completely fall apart under unsteady conditions, which, let's face it, is how we actually use our devices. They can't handle it if you accidentally drain the battery way down, and most of them are custom-built for one specific battery, which is expensive and not very useful for anyone else. We really needed something better, something more fundamental.
And this is where our story gets really interesting. A team of researchers had a brilliant idea. They decided to stop looking at the battery as just a super complicated chemical puzzle and start looking at it through the lens of fundamental physics.
So the old way was to get totally bogged down in the weeds, trying to track every little chemical reaction. But this new approach, it zooms way out. It suggests the answer isn't in all those tiny details, but in one of the most powerful laws in the entire universe, thermodynamics. And the biggest clue of all? A little concept called entropy. So, what in the world is entropy? Well, scientifically, it's the official measure of disorder, or disorganization, inside any system. When a system gets more disorganized, we say its entropy goes up. But let's make it way simpler. Just think of entropy as messiness. That's it. A perfectly clean, organized room has very low entropy. A super messy room? That's got high entropy. And guess what? As a battery gets used, charged up, drained down, over and over, its insides get more and more disorganized, more messy.
And this simple idea leads to a truly groundbreaking theory. What if the death of a battery isn't just some random process of decay? What if the capacity it loses is directly tied to the amount of messiness, the disorder that's been created inside of it?
And boom, that's the core idea right from the research paper. They call it the Degradation Entropy Generation Theorem, or the DEG theorem for short, and it says exactly what we were just talking about. There's a direct, predictable relationship between how much a battery is degraded and how much entropy or disorder has been generated inside it.
It all boils down to this one beautiful, simple equation. For the very first time, we have a formula that says degradation is basically just a constant times the total amount of entropy you've created. The messier the battery gets inside, the less charge it can hold. It's just this elegant physics-based reason for why our batteries die.
Now, of course, a cool theory is one thing, but you've got to test it. And to really see if they were onto something, these researchers didn't just run some normal tests. Oh no. They designed an absolutely brutal, abusive stress test.
And just look at their lab setup here. It doesn't look like some pristine, sterile lab, does it? It's kind of messy itself, which is actually perfect, because the whole point was to create total chaos inside these little lithium-ion batteries. They were going to push them to their absolute breaking point and then keep pushing. And I mean, this test was a gauntlet. They hit the batteries with totally inconsistent charging cycles. They deliberately drained them way below the official safety limit, in some cases all the way down to 0.6 volts. That is basically battery torture. The whole thing was designed to cause the exact kind of rapid, chaotic damage that those old models could never, ever predict. And here's what that chaos looked like in the actual data. The voltage, the current, the temperature, it's all over the map. This is the messy, unpredictable real-world behavior that their new simple thermodynamic model had to make sense of. Talk about a challenge. So, after all that abuse, after generating all that chaotic data, the big question was still hanging in the air. Could their simple entropy-based formula actually predict the damage? How did it do? So this was it.
the moment of truth for their whole theory of disorder. How did the prediction actually hold up against the real-world results?
The result? Almost 100%. The model's predictions matched the actual measured damage to the batteries with nearly perfect accuracy. I mean, it wasn't just close. It was a direct hit.
And this beautiful plot is the proof. Out of all that messy, chaotic data from the stress test, the model found this: a simple, clean, linear plane. It shows that the battery's capacity faded in perfect proportion to the two main types of entropy, or messiness, it generated. The model found perfect, simple order hidden inside the chaos.
So why is this such a huge deal? Well, first, it's a universal model. It should work for pretty much any lithium-ion battery. Second, it's based on the fundamental laws of physics. It's not just some fudge factor they came up with by fitting a curve to the data. Plus, it works using just 3 simple things we can already measure: voltage, current, and temperature. It's a powerful tool that can see failure coming even under the absolute worst conditions.
Which leaves us with one last, really exciting thought. If we now know that a battery's death is directly tied to the amount of disorder we create inside it, if we can perfectly predict the end, does that mean we can use the same key, the idea of minimizing entropy, to finally unlock the secret to giving our batteries a much, much longer life? That's the amazing question this research leaves us with. Thanks for tuning in.